Welcome all to the U.S. Department of Energy's SBIR, STTR, Fiscal Year 14, Phase 1, Release 1 Topics webinar. My name is Chris O'Gwin, and I am moderating today's meeting. In just a moment, you'll hear directly from Manny Oliver, the Director of the Department's SBIR, STTR Programs Office. He'll provide you with some basic topics information as it relates to this Release 1. Following Manny's discussion, you will then hear from the managers that oversee these topics, topics 29 through 40, as they clarify their expectations and answer questions regarding these subtopics as received from many of you during the registration. Also during the presentation, we will take your questions, not orally but via the on-screen chat text box that you see at the bottom of your screen. So as you are hearing from these managers, feel free to please submit and type in any topic-related questions you may have into the chat box as you see it again at the bottom there. We will group these and we will present these questions as they come in to each topic manager following their presentation. Just a reminder, your questions should be related to the topics, and any questions you might have in regards to the funding opportunity announcement that will be associated with these topics you should hold off on asking those during this webinar. You are, of course, free to ask those questions during or at any time after the webinar. You can go ahead and give us a call, or you can shoot us an email, or you can wait for the funding opportunity announcement webinar that we will be putting out shortly early next month. So what you see here is following the webinar, there will be a link provided to all registrants. It will be emailed to you automatically, so you will get a copy of the link to the recorded webinar following this. So let me introduce you to Manny Oliver.
Thanks, Chris. And so just over the agenda, I'll probably spend about 10 minutes just giving an introductory discussion of our topics. And this is primarily targeted to people who are new to our program, so that when you're reading through our topics, just give you some ideas of what to look for as you're reviewing those. We've made a couple of changes in the last couple of years, so I'll talk about those as well. But the bulk of today's webinar, you'll be hearing from DOE program managers talk about their topics from two of our programs, the Office of High Energy Physics and the Office of Nuclear Physics. Next. So in terms of the Phase 1 announcements we're going to be having for fiscal year 2014, will be similar to last year. We'll have two Phase 1 announcements. We call them Release 1 and Release 2. In Release 1, we'll have 5 of the offices from the Office of Science and the Office of Defense, Nuclear, Nonproliferation. In Release 2, these will be primarily our applied energy programs and the Office of Fusion Energy Sciences. So the one change we made versus last year, for those of you looking for fusion energy topics, those will not be in Release 1 this year. They will be in Release 2. The next slide, we have our schedule. Again, we issued our topics for Release 1. These are the schedules for both Release 1 and 2. I'll go through the one for Release 1. So we issued our topics last week, and we're holding a webinar this week to allow you to discuss any questions with program managers, and you can certainly continue to contact them by email after today's webinar. The funding opportunity announcement will come out August 12th. We'll also have a webinar associated with that. So those are your questions related to the planned funding amounts and how do I apply and those type of things, really appropriate after we issue the funding opportunity announcement. Right now, with the topics out, it's really a chance to figure out if there are topics that align with the technology areas that you work in to see if there's an opportunity for you to submit an application. We do have a letter of intent requirement. That's September 3rd. That's a mandatory letter of intent, so please be aware of that. If you intend to submit an application, please do submit a letter of intent by the 3rd. And the details for submitting that, of course, will be in the funding opportunity announcement. The full applications will be due on October 15th. We plan to notify you in early January, and you would start your grant in February. And as I mentioned, soon after our funding opportunity announcement comes out, we'll be having a webinar for that. So we'll, again, just provide a general overview of the DOE SBIR programs and hold a Q&A to answer your questions, specifically about the the Phase 1, Release 1 funding opportunity announcement. So just discussing the topic basics, some of the questions we usually get in terms of where do our topics come from. So those are created by DOE program managers, and typically they are looking, they have, to support their mission, there are some needed technology breakthroughs. They do that in consultation with experts throughout the country, including DOE labs as well as universities and even industry. So those are, and our program managers do span, in many cases, broad technology areas. So one of the things I would point out is they may not be able to answer all of your questions directly on the call today, but should be able to get back to you with an answer if they need to reach out to some other experts at DOE or outside of DOE. And again, our topics are organized by program offices, 2 of which we are going to present today. And we do list the DOE program managers with each subtopic within the topic. The purpose of the discussions kind of at this stage are really for the program managers to clarify what they're looking for. How broad is the topic? What would they consider as being responsive? So they're certainly here to help clarify that. But we do want to point out, the decision to apply is really yours. You really shouldn't be asking program managers, should you apply? That's really, your decision based on your understanding of the topic and the, innovation that you're proposing. So the next slide, we have an example topic on the right side of the slide. I apologize, it's a little compressed. The important things to point out, especially if you're new, is that, all of our topics are numbered and each subtopic has a letter. So this is topic 7. There are 3 subtopics here, A, B, and C. It's very important when you submit your letter of intent and your application that you specify the topic and subtopic. We don't, assign those 2 applications, and those are only going to be reviewed under the topic and subtopic that you submit. And we will decline the application if that is not specified. There is a new topic header this year. That'll list the award amounts that are available under Phase 1 and Phase 2. This year we've also added additional information indicating whether we're accepting SBIR and STTR applications and fast track applications. So please look at the header when you're submitting an application. As I mentioned, under each subtopic there is a DOE program manager with an email. You're certainly free to ask questions today, but also contact them by email with any additional questions. And again, a lot of times you may want to talk about something that's somewhat proprietary in terms of your innovation. May not be appropriate to ask those questions in an open venue like this today. So those would be a good opportunity to submit by email. There is an other subtopic with each of our topics. The intent of this is really to slightly broaden our topic innovation areas. If you have something that relates to the topic but does not fit within the subtopics, again, it would generally be still in the area of the topic. So don't read just the title and assume that anything that fits in the title would fit. Read through the topic header, look at the other subtopics to get a feel for what the innovations we're looking for. If it doesn't fit exactly in those subtopics, you can submit under other. And again, over the past few years, since we've had the other, about 6 to 9% of the awards do go out under other, so this is not there just as a placeholder. We do make awards there. And finally, our program managers do take the time to put in references. This is not for all of our subtopics and topics, but for many of them, this is an attempt to help you get up to speed on what's going on in these fields. So we do encourage you to look at those references before you submit your questions, because some of the information, useful information is there. One of the new features we introduced last year were tech transfer opportunities. So these are very different than our traditional topics where we ask for a breakthrough and you submit new ideas to address them. In this case, we've, what's happened is we've funded our, research at a DOE lab or university, and their inventions have been created as a result of that research. And in most cases, that is in the form of an issued patent. In some cases, they're patent applications. And what we're looking for you to do as an applicant is not really to invent something, but to take one of these inventions and complete the R&D and drive it to commercialization. So in addition to your normal grant, you will receive an option to license the technology. As you move forward, you'll have to convert that option to a license when it's appropriate as you're completing the research in either Phase 1 or Phase 2. So more information about this is at the beginning, I believe, pages 2 and 3 of our topic document. So if you're planning to apply to any of the tech transfer opportunities, please review that information. So here's an example of a tech transfer opportunity. We do label these. So in this case, this tech transfer opportunity is for the entire topic. And I just picked up the first subtopic A here. One of the things I would want to point out is that under a tech transfer opportunity, the research organization that's sponsoring the tech transfer opportunity is also clearly labeled, and there will be contact information for the tech transfer office, the links to any patents that have been issued or any patent applications that are pending as well. And maybe in some cases the lab will have a link to the tech transfer opportunity on their website. So please, any questions, technical questions with the status of the invention, are there any research reports, please discuss that with the National Lab as opposed to the DOE Program Manager. We will also include the DOE Program Manager there, and any questions related to them would be more general in terms of, well, I'm going to plan to do this with the TTO. Is that what you're looking for as responsive under this topic? Many of the topics do describe what the DOE program is looking for out of the TTO, so you should contact them with those questions. And on my last slide, I just want to point out we are continuing the fast track applications that we started last year. Again, fast track is a combined phase 1, phase 2 application. And again, more details about what's required for that application will come out with the funding opportunity announcement. And just point out that we don't expect a large fraction of the applications to be fast tracked. We do have a lot of very high-risk exploratory research in phase 1. It's very hard to do a combined phase 1-2 if you're not sure what phase 2 really looks like until you have phase 1 results. So we do expect the majority to be regular phase 1. Maybe as many as 5 to 10% of the applications might come in as fast track. For last year, only about 4% of the applications were fast track, and the award rates for fast track and our phase 1 applications were similar. So that's all I had on the kind of an introduction to our topics. Again, more information will come out with the funding opportunity announcement. If you have any questions that are more general nature, not related to does your innovation fit with a certain topic, but just about the DOE program, please visit our website or contact us by email or phone. The information is presented there. I'll turn it back over to Chris.
Thanks, Manny. And let me remind you, if you have any questions as the topic manager, and in this case we have every topic manager that is responsible for overseeing these topics speaking today, so you have an opportunity to directly text your question and hopefully get it answered today. If not, you can send your email off to these folks at any time during the open solicitation here. So we're going to begin with the High Energy Physics program, and we're going to begin with topic 29, High Energy Physics Computational Technology, and we have Larry Price on the phone. So Larry, the floor is yours.
Okay, thanks. Hello, my name is Larry Price. Let me just say very briefly that the next several topics will have to do with the Office of High Energy Physics. High Energy Physics deals with investigating the most fundamental components of matter and the interactions between them. We do this with typically very high energy beams, but also using other techniques. And again, often, but not always, we do these in large collaborations, at least on the experimental side of things. So I'm talking about topic 29, which has to do with computing in high energy physics. And again, just a very brief introduction to the topic. As in many walks of life today, computing is absolutely central to particle physics. We use it to take our data from our very complicated detectors. We use it to analyze our data. We use it to predict what we're going to see, to calculate the results of theories. So there are many ways in which we use computing. A topic related to computing, which is getting a lot of attention these days and is very important to particle physics, is the question of data. we generate very large amounts of data, often measured in what are called petabytes, 10 to the 15th bytes, 1,000 trillion bytes as a typical number. An experiment these days in a year can generate many of those petabytes of data and have to deal with them, and often have to deal with them in many different places around the world because the collaborations are big. So in computing, we have 8 subtopics and the 1 additional general subtopics. Let me touch on them extremely briefly, at least mention their names. I'm sure you've all seen them. But distributed computing, that has to do with the extended nature of our collaborations. With even on a big international collaboration, maybe 40 sites in the U.S. may be involved in dealing with the data, plus many more around the world. We need to be able to compute and move our data around in a number of different ways. And so we're interested in software that enables us to do that, in particular things like middleware for grid-enabled systems, but other techniques also. Somewhat in the same mode, topic B is, I'm sorry, I scrolled off here and I have to just look at the right title, Collaboration Software for Distributed Computing. Many different groups, often in different places, are trying to work together on the same experiment, either to design it or to look at the data. And so innovative techniques that allow us to do that in an efficient way are important. Modular software performance monitoring, that doesn't necessarily have to do with the multiple locations, but it has to do with looking at our very complex software and knowing how well it's working, being able to figure out where in the software we can do better. Topic D, data frameworks and database development. Again, we deal with lots of data, and we need often clever ways, innovative ways, better ways of dealing with that, and with the databases broadly defined with which we handle our data and the metadata attached to them. Topic E, geometry description for HCP software. We build very complicated detectors and devices often. And our software, whether it's simulation or analysis, needs to be able to know where all the elements of the detector are, and often to be able to do that from more than one program for the same detector. So we'd like general ways, which we actually don't have. We have ways for individual programs, but often not in a general way that we can take, for instance, a CAD drawing and turn it into something that many of our programs can use. Topic F, parallelization of software and simulation tools. That's obviously a very important topic for computing in general. We want to be able to make use of the latest technologies in computing, and many of our codes are lagging behind because they were developed a little bit earlier. Topic G is a little more specific, enhancing the JANT4 simulation toolkit. This is a very important tool that we use to simulate how perhaps events that we haven't yet seen or haven't yet detected, particles that we haven't yet detected, will look in our detectors or in other ways that we look at events. And it's a quite large code. It needs to be parallelized, for instance, as in the previous topic, but it can use other ways to improve its performance and improve its physics accuracy. Topic H, data and software preservation. This is sort of the end of our life cycle of an experiment, becoming very important these days. It's always been important, but the data is bigger. We need to preserve our data so that it can be looked at in the future still if we have questions about the results of a particular experiment. And we also need to preserve the software so that we can run it as computers evolve, and that's often more challenging even than keeping the data in some place. Okay, those are the basic topics. There are a few references. There were a few questions that were submitted, most of which I think are either rather general or hard to answer in this context. I think I'll just pick out the ones that seem as if I can answer them, and maybe if people are on who think I didn't answer their topic and could have, you can raise your hand again. So one is, how can private business encourage government labs to help? Well, the way I would answer that is to say that we encourage people submitting these SBIR proposals to work with researchers in the field. Labs are often a concentration of technology and a place that you want to partner with, but not only laboratories, also universities that are involved in the field. And there's something where we can be helpful on an individual basis if you want. You have my email address if you have a particular topic and would like to know who in the field is working on that and might be someone to contact. I would say use my email address and we can try to be helpful. Otherwise, look on the websites for the national labs that do high energy physics. Maybe somewhat similar, there was a question that read, how do we get in touch with the leader of the project? That's a little unspecific, but if you think that there's a specific topic or experiment or other type of project in particle physics that you could help develop technology for, probably I'm the right conduit again. You can tell me, I've heard about this project called LBNE or something. Who can I talk to know whether my technology is right for them? And I can probably help you put you in touch. Another question was, what are the websites I could visit to know more details about the topics? There were a few references in the solicitation. I think the most useful, it unfortunately does have a lot of information, but I don't think it's too unreasonable to ask you to look through the topics and pick out the individual ones, was the reference to the online site for the Conference in High Energy Physics, International Conference in High Energy Physics, held last year in 2012. And on that site, there's a program of the talks that were given, and in almost all cases, a link to the presentation either in PowerPoint or PDF format. And I think you can correlate the topics that are in our solicitation with the titles of those talks, and then go to one that's on the right topic. And I think you'll actually learn a lot by rummaging around and looking at some of the other talks about generally what people are worried about in the computing area for high energy physics. I'll just mention this last question, which says, I'm interested in topic 29G. Why is it not listed above? I probably don't know the exact context for above, but of course 29G, as far as I know, is in the solicitation, and that's the one about enhancing the GEONT4 simulation toolkit. It's one that probably may attract the most interest, in fact. So I think I'll stop there and see if there's anything else.
That's good, Larry. And this, topic G should be in there. I'm looking at it on my list right here. It's evident. I'll go ahead and verify that while others are speaking. But there is one question here, and it's in regards to G as well, topic 29G. And it says, usually GEONT4 simulations can be run in parallel on massive clusters. What additional aspects of parallelization would you like to see?
I think, as I understand the question, we do a lot of what we sometimes call trivial parallelization of GEONT and a number of other programs that we use, where we basically have almost independent computers that take on one event or one stream at a time and do them without talking to any of the others and without breaking the problem up any more than the event structure that's typical of high energy physics would allow. So that kind of parallelization is done routinely. It's extremely important. We could never get enough power out of a single processor to run the program and get enough results. But what we're interested in now is the flood, I would say, of new technologies in computing that are more inherently parallel, just starting with the basic CPU cores for commodity computers that now typically have 2, 4, 8 processors on one core, with perhaps less memory per processor than we're typically used to. We do use those multi-core processors that are what you buy these days. You almost can't buy a computer without them. But we don't use them terribly efficiently. We'd like to do that better. Even more so, supercomputers, high-performance computers, such as are provided by the Department of Energy to our programs at NERSC, by the NSF in various places, that are intrinsically parallel and rely on excellent communications between the processors. Those we're just beginning to use and exploring how to use. JAD4 in particular does not use them efficiently, and we would really like to be able to do that. As we look to the future, we think that more and more really intrinsic parallelization, where perhaps one event is divided up into multiple parts that have to talk to each other through the interconnects that a supercomputer provides, for instance. So that's the general idea.
Great. Larry, thank you very much. And we have clarified, or we have verified that, yes, 29G is on page 110 of our topics document. So if you've missed that, you can just turn right to page 110 and you'll find the subtopic description and references for topic 29, subtopic G. Larry, we'll go ahead and move on to topic 30. Thank you very much. Topic 30 is Advanced Concepts and Technology for Particle Accelerators. And we have Eric Colby on the line that will be discussing topic 30, and he will be handling 31 and 32. So we'll begin with 30. The floor is yours, Eric.
All right, I appreciate that. This is Eric Colby, Office of High Energy Physics. And as he mentioned, I'll be discussing the advanced concepts for technology for particle accelerators, the radio frequency accelerator technology, and the laser technology R&D for accelerators topics. That's 30 through 32. What you no doubt have noticed is that this year there has been a reorganization. It has two aspects to it. In the prior year, there was a solicitation broken into advanced concepts for the energy frontier and for the intensity frontier. For clarity of process, these have been merged into a single topic. This is topic 30, Advanced Concepts. And what we've done is where technologies are being, topics are being put out that are very specific to an accelerator project, such as the muon accelerator project or mu to E, is we have labeled those topics with references and by name what their associated accelerator physics project is. And that way you can see clearly subtopic by subtopic which of these associates to a specific project and which is more general. In the area of advanced concepts, the first 7 of the topics in topic A. So this is Advanced Accelerator Concepts and Modeling, and you see there are a series of topics that are numbered 1 through 9. The first, 1 through 7, we are seeking revolutionary new capabilities. And in general, these are a push to develop accelerating or bending techniques at much higher gradients than currently available. And for the reason that that would benefit high energy physics, we also expect that has the potential for commercial applications in more compact industrial, medical, and security accelerators. So topics 1 through 7 under 30A are, these are looking for revolutionary new capabilities. Under topic A, the two subtopics 8 and 9 are very specific to the projects mu to E and project X. And you're urged to take a look at the references that are included therein to understand the specific technical needs for those two projects. And again, the expectation is that incoming proposals will be responsive to the actual project specifications in each of those cases. Moving on to 30B, Advanced Concepts and Modeling for the Muon Accelerator Program. There is an extensive set of topics ranging from design to taking a look at specific aspects of overall machine optimization. And again, you're urged to take a look at the references specific to the Muon Accelerator Program and to some of the prior art that is indicated in the references for this subtopic. Subtopic 30C, Computational Tools and Simulation of Accelerator Systems. This ranges from developing user interfaces and more error-tolerant packaging for codes that have existed to adding upgraded physics capabilities and addressing new classes of physics problems with these codes. In several instances, there are references included where there is a desire for new physics that gives an indication of what physics is desired for those codes. Topic 30D, Particle Beam Sources, Electron and Ion. These are quite project specific. I refer you again to the references. One is for electron sources, primarily for FELs, and the second is for Project X. And topic E, the last of the specific topics in this section 30 is Novel Device and Instrumentation Development. And these are, again, highly specific to Project X. What you'll find at the end of this topic 30 are not only the specific subtopic references, but general references. I would urge you, as you think of other potential proposals, if you are going to submit under 30F, the other category, please take a look at the references and ensure that, that the proposal that you are submitting is responsive to the current state of the art and the current challenges that are outlined in those references. And I'm happy to take questions in just a moment on that. Moving on to topic 31, radio frequency accelerator technology. So in this area, this is generally meant to aggregate together work on pulsed power technologies, that is modulators, high voltage supplies, klystrons, TWTs, components necessary for the generation of radio frequency power for accelerators. And so as with the prior topic, what you'll find are under topic A, 31A, radio frequency power sources and components, the first 5 of the topics listed here, beginning with high gradient research and development and ending with low cost radio frequency power sources for accelerator applications. These are again of a general nature looking for revolutionary new capabilities. Topics 6 and 7 are quite specifically project motivated, in this case motivated by Project X, and you're urged to take a look at the references and understand clearly the project requirements. The same holds for 8. Under B, pulsed power systems, this is very specific, desire for a replacement for a thyrotron tube for a very specific application. Please refer to the specification document therein for the details. Topic 31C, deflecting cavities. Again, very specific to Project X. Please take a look at the specifications. And as with the other category in advanced concepts, please take a look at the general references at the end of the section to get a clear idea of what the priorities in the current state of the art and challenges are to frame possible proposals in the other category. And please get in touch if you have questions or want to discuss further. Moving on to topic area 32, laser technology R&D for accelerators. This is a new topic area within the Office of High Energy Physics. It has been introduced because lasers are playing a growing role in the accelerators used for high energy physics and beyond. And what you'll find within this section is a fairly focused effort on what are called ultra-fast lasers, that is lasers producing pulses a picosecond or less in duration at high peak powers, at high average powers. So it is a narrow niche for this particular case. And that's a key point, that this is not a broad solicitation for any laser technology. To give a more concrete illustration of the types of technologies that are sought, there is a table that has been included on page 124 of the solicitation under what's called subtopic A, ultrafast infrared laser systems at high peak and average power. This table lists 4 types of lasers that are sought for specific accelerator applications. I won't talk through them in detail, but please refer to this table. All of the subsequent subtopics are seeking technologies that will enable one of these 4 basic types of laser. So each of these refers back to this table in asking for work to be done either on coatings or timing synchronization or so on. These are all apropos the 4 types of laser that are in this table. So please refer to it as you consider writing a proposal. In this section, again, there are a couple of references provided. One in particular, the very first of the references, is Workshop on Laser Technology for Accelerators. Please take a look. This will give a clear sense of the applications that are referred to for these 4 types of lasers and the specific challenges. With that, let me turn to the questions that were typed into the web page. So the first of the questions was, what is the future of the area of scientific study for topic 30, advanced concepts? The brief answer, recapping what I've said, is topics 1 through 7 are meant to be long-term revolutionary advances. They are investments in significant advances in the technology. Topics 8 and 9 are quite specific to projects, and similar comments apply throughout section 30. You'll see both investments in revolutionary advances in technology and then very specific project-oriented requests.
So Eric,
yes.
how would one proposal respond to? Can one proposal respond to multiple items within 30C, or would it be would they be responding to just one item in each of those?
So within 30C,
how do you handle that? What's your recommendation on how a proposal should be submitted to 30C that has multiple areas?
So the immediate response is, since you chose 30C, which is computational tools and simulation of accelerator systems for the question, the response is these would lend themselves potentially to having more than one numbered subtopic included in one proposal. And of course, the immediate question is, does the scope of work fit within the footprint of the SBIR program? If it does, then there is no issue with including tasks that are responsive to more than one of these numbered subtopics.
Okay.
All right. Let's see. So of the other questions that were asked, is there any interest in, so this is with respect to 30A, is there any interest in proposals on compact FELs and undulators? Short answer is, again, we're always looking for revolutionary new concepts. However, please take a look at the references, understand the prior art, and please get in touch to discuss the idea, and we can explore that a bit further. The question was, how do we collaborate with DOE National Labs? How can we proceed? There are a number of web resources available. I would refer you, in this case, to the acceleratorsamerica.org website. Therein you'll find a tab which says Working with the National Laboratories. It is effectively a portal site that links to the accelerator laboratories and is a way for you to get into those labs and understand potential partnership opportunities. There's some very specific topical questions. I'll be happy to take those offline via email rather than with a general audience. Let's see. And at this point, I think I've responded to the general questions that have been asked. So are there any other questions?
I think that's all we have for now, Eric. That one last question. I appreciate your insight, and anybody who does have any further questions for Eric, please go ahead and send it right to that email that you see on your screen. That would be for topics 30, 31, and 32. So thank you, Eric.
Certainly.
Let's go ahead and we'll move on to topic 33. And topic 33 will be superconductor technologies for particle accelerators, and we have Ken Markin on the line. Ken?
Good morning. This is Ken. I'm with High Energy Physics here in Germantown, Maryland, and topic 33 has been reorganized somewhat this year in that we've combined all the superconductor-related topics. So previously, superconducting RF was included in the separate advanced concepts topics, and we've changed that somewhat this year. So topics A, B, and C are related in that they're all aimed at our mission need for higher field superconducting magnets. So all of these are really interested in the materials, the cables, the magnet technologies that will get us to higher than state-of-the-art field levels for accelerator projects and applications. For dipole magnets, this is roughly higher than 20 Tesla. For solenoids, I would say it's 30 Tesla and higher. So both the wire needs and the starting raw material needs all feed into our need for higher field magnets. Of course, higher fields bring higher stresses, so a critical part of the technologies relating to these three subtopics are high field wires and cables that have high strength. Also, I would like to emphasize that for superconducting wires and strands, we need lengths. We need lengths that can build magnets. So I would say minimum kilometer lengths. You can see the specifics that we have put in the topic language, but we need kilometer and longer lengths with high critical current density and high strengths for high field performance. So that's sort of my general summary of what we're looking for in the subtopics A, B, and C. I will mention that looking ahead, the primary projects that we see in the long range that are going to need these are the high energy upgrade for the LHC. And let me just remind you that that's an upgrade project that goes beyond the immediate need for high luminosity. So there's a high luminosity upgrade for LHC, and then beyond that in the future is a high energy upgrade. And we are looking at high field magnets for the high energy upgrade for LHC. And also there's a whole suite of high field magnets that are needed for a future muon accelerator in the U.S. This is a program that's in its infancy in the U.S. program, but we expect to grow in coming years. So those are the two main mission drivers, are the muon accelerator and the high energy upgrade for LHC. In thinking about those projects, I would say it's most likely that we're going to need high temperature superconductors to go to the field levels of interest. And there are specific problems with the two major classes of high temperature superconductors. The first of these is BISCO 2212. We're already investing in this area, but there are problems that need to be solved. The second is rare earth barium copper oxide conductors, sometimes called 123 conductors, or IBCO. And just very briefly, I will tell you that our research priorities for BISCO are there's a great need for better mechanical properties. The wire that we have today is not particularly strong, and to be used in large high field magnets, we're going to need both conductor and cables that are stress and strain tolerant. So that's an important issue. If any of you follow the literature, you'll know that in recent years, significant advances in high field performance have been achieved in BISCO 2212 by overpressure processing, high temperature treatment in high pressures of oxygen. These are done today on a very small scale, but if this technique is going to be used for large magnets in the future, we need to think about methods of high oxygen pressure processing that can be scaled up to cable and coil heat treatment. So that's another important issue for BISCO 2212. For REBCO or IBCO research, I would say a high priority is conductor that can control magnetization losses. So today these are wide flat tapes. We need to think about technologies that will give us filaments in these materials. We need to think about transverse strain tolerance. Today these are pretty strong in longitudinal stress, but there are issues with transverse stress and strain tolerance. Piece lengths are an issue. Today the materials that we get with coated conductors are relatively short. We need to think about ways to process them to magnet scale lengths. Cost and performance ratio is going to be an issue, and specific defects remain a challenge in these materials. So any processing methods that address these are very important to us. Moving on to subtopic D, superconducting RF materials and cavities. For superconducting RF, the need remains for higher accelerating gradients while retraining high Q in the cavities. So there are very specific targets that are listed in the topic. I'm not going to repeat them. You can read them. And our present understanding is that the cavity materials, properties, and characteristics do strongly affect cavity performance. So we're very interested in better materials processing and characterization methods for the cavities. And we have specific target frequencies and gradients and components, again, that are listed in subtopic D. So I will leave that to you to read those specifics. These are from the reference design for Project X. That project has both CW and pulsed sections, so we're interested in superconducting RF for both continuous wave and pulsed applications. Also, I will remind you that we have a growing interest and need for our what I will call our stewardship mission. So we are interested in accelerator applications of these technologies for things other than just particle physics. So medical applications, industrial applications of these technologies, accelerators that are important to them are also of interest to us. So the final product does not necessarily have to be a particle physics accelerator. So we also list subtopic E, cryogenic and refrigeration technology systems. As always, our main interests here are higher efficiency, lower cost systems. The cost of the cryogenic systems in large accelerator systems is always significant, so we are interested in any technologies which enable us to bring them under control. There are also, for superconducting RF cryo modules, specific opportunities to improve integration or interface with the cavity strings and other RF components. As you might imagine, we need precise control of an accelerating string that includes multiple cavities and all the other RF components that go into that. And these alignment systems need to be integrated into the cryo module, so there's room for improvements there. Subtopic F, ancillary technologies for superconductors. You can imagine a range of things, but I would say the primary mission needs that stay with us are insulation and epoxies for magnets. So thinner insulations that are compatible with the superconductor processing temperatures and with the epoxy impregnation processes. And they have to also be stress and strain tolerant and radiation tolerant in the environments that we need them. So those are the general areas, and you can see more specifics in the topic language. So those are the general comments that I have addressing the specific questions that were submitted upon registration. One question that we had is embedded fiber optic sensing and desired technology for strain and temperature measurement in superconducting magnet coils of interest. And yes, absolutely. We continue to make investments in a range of diagnostic instrumentation technologies, including fiber optic sensing. So this is an area of interest. Another question specifically addressed to SRF cavities were our cavity diagnostic tools, such as new temperature mapping ideas, included in subtopic 33D. And yes, absolutely. Any diagnostic tools which help increase the performance or reduce the cost of these systems are of interest. If the focus is solely on diagnostics, then I would suggest that some thought needs to be given to the commercialization path. I presume that would have to include a partner for the cavities or the cryo modules, so just keep that in mind. But the diagnostic tools are absolutely of interest. And we also had a specific question on 33E, that is, would more efficient heat exchangers as components of these cryogenic systems be of interest under this topic? And yes, again, any methods for increasing efficiency and reducing costs are of interest, but I would again make the same caution, and some thought needs to be given to a commercialization path. What will your market be for subcomponents of these systems? So those are the specific questions we received. Looks like there's some others that have come in.
There is. We do have a couple questions. Let me read these out loud. Is there a way to get a baseline of where the DOE stands in regards to cryogenic refrigeration systems? I believe that would be in regards to topic 33E.
That's definitely 33E, and let's see. I guess we did not have any specific references. Oh, yes, we did. Okay, so there are a couple of general references to the Cryogenic Engineering Conference and to the Applied Superconductivity Conference, both of which are very recent. And these links will take you to, I think, the programs there. So some perusal there. If you have specific questions regarding the state-of-the-art of cryogenic systems, you can email them to me, and I will try to get you to a better reference in that regard.
Okay. And this is more of a general question, and I'm not sure which subtopic. It may be E or F. What has already been done? What is being researched? And more specifically, what is DOE looking for? If that's too general for you,
that looks like it was a follow-up to the previous question, Chris.
Okay.
And so I think we can move on to the next.
Yeah,
okay.
Again, I would just say look to the most recent literature, and specifically Cryogenic Engineering Conference and Applied Superconductivity Conference will give you a good picture. If you peruse those proceedings, will give you a good picture of the existing state of the art.
And then we have one last question. Why don't you read that out loud, Ken, from Lessig there?
So subtopic A
yes.
is requested niobium-310 in fields of 15 to 20 Tesla. Will you accept a proposal on niobium-310 with higher upper critical field? Well, higher upper critical field certainly has the potential to give us higher field magnets, but I think you need to, in your proposal, address exactly how it will get us to higher field magnets. So yes, you can potentially see that that would be a benefit, but unless it gives you higher critical current at the fields of interest, then higher critical field alone, I would say, is not going to get us to a magnet technology. So that's my view on that.
Very good. Ken, thank you very much. And again, any questions for Ken, please send them specifically to his email address as listed on the screen and in our topics document. We'll move on to topic 34, which is high-speed electronic instrumentation for data acquisition and processing. And I believe we have Peter Kim on the line to discuss topic 34.
Yes, hi. My name is Peter Kim from the Office of High Energy Physics, and I'll be going over the topics 34 and 35. 34 is the instrumentation for data acquisition and processing, and 35 is the particle detector, high energy physics detector and instrumentation. They are somewhat related, but we separate into two separate topics. So let me start with the, we are in experimental particle physics, where we detect the interaction of the elementary particles. We build a detector, and we see how they interact. And as you know, we can have elementary particles created in early universe in nature, or such things as supernova. Or, as we just went over last half an hour, it can be created in an accelerator. And as you know, the discovery of the Higgs at LHC recently is a good example. So the particle physics detector has been in development for, let's say, about 50, 60 years. And over time, things has become very complicated, and it requires a very fast without a large size of detector, and therefore the instrumentation has become very important. And topic 34, we have a 40 foreign subtopics, and the first one is special purpose chips and devices. Number 2 is circuit and processing data. Third one is the systems for data analysis transmission. And the last one is the enhancement of interconnection systems. I will not go into the details of these items, but let me first point out that these are some examples, and any applications related to instrumentation in high energy physics can go into the other, the last one, topic 34E, and that will be considered. So therefore, you're not limited to any particular specific mention in here. And the idea is that the electronics has made a great progress in the recent years, and we like to tap that into our particle detector instrumentation system. And so, for example, the special chips that now we have, the CPUs are down to 28 nanometers and so on, but most of our particle detector special chips are still at 130 and now going into 65 nanometer level. And that's an example where really close work between the physicists at national labs and universities can work with the industry to find the special purpose chips that will be really suited for particle physics detectors. And also, we are looking into various data DAQ system and transmission that can use the industry development follow. We're not trying to reinvent any wheels, but there's great progress has been made, and we'd like to use that. For example, would be such as some new ideas in optical links and or the wireless, even wireless transmission. And I will go on to the topic 35. So we have now we have a large detector systems built and instrumentation. And here again, these are examples of subtopics. So we need to detect the particle interaction with our detectors and identify what kind of they are. And then we have a special separated photon detectors, because the detection of photons are somewhat different from others and requires dedicated sensors. So that's separated as a 35D. And the new area that we've been involved more in the cosmic frontier is that we are now looking for very, very faint signals in our detector, and that requires that the background, low background, is absolute necessity. And so topic 35C and, for example, 35E deals with the detector systems where you need to cool the detector very cold, for example, or you need to have very radio activity pure detector components, for example, so you can detect signals down at few kV level. And 35D is actually, it's been there for a long time, is when we have high energy accelerators, there are a lot of collisions and your devices need to be radiation hard. So this is, for example, any space-based electronics would be need that. And we've been using a lot of that technology developed already. And but as we go to the next generation of particle physics detectors, we need to have even more radiation tolerant components. And the final item is that as we are detecting particles, and we like to detect the particles as they're created without interacting material without any sensor. And let me put it this the other way. So you want to detect the particles that will get to your the detector component in a pristine condition before being deflected or some other material going through. So that has come into a big endeavor into building very light material inside detectors inside. Therefore, they are like a carbon foam or various things that therefore the detector can be very light and also preserve the information that you originally started from. And there is also another the 35G. It's other. So please consider that other means if you have any great ideas, then you're not restricted to any of the listed 6 topics before that. Okay. I have a few questions from SPIR office that's been transmitted to me, and they turned out to be more or less in general in nature, such as some basic requirements and so I think that, for example, that for the basic requirements, I think I suggest to read the FOA carefully, and there are deadlines. You must meet the deadlines, and if you follow the instructions, that should be fine. But if there are more specific questions, I'd like to please send me an email. And there were some other more generic questions, such as we have done phase 1 and phase 2 what previously in a similar topic. Can we still apply? Yes. If you have a new innovative idea, then you should. And for example, another one was are you looking for only components only, or we are specializing in a more fully integrated, ready-to-use device? So that's the answer is yes. Of course, if you can work with the existing labs, university groups, and can design an integrated device, that's of course allowed for the application. And another general one was, is this only for fabrication testing? But no, any modeling or experimental research is welcome, as long as that will lead to the benefits of particle physics and also lead to successful commercial product at the end. So that's all I have. If you have any further questions, let me know.
That's excellent. Peter, thank you very much. And that was topics 34 and 35, and that rounds out all the topics for our high energy physics program. So we'll go ahead and move on to our Office of Nuclear Physics topics. And first topic on that would be topic 36, Nuclear Physics Software and Data Management. And we have on the line Manasher Farkande. Manasher?
Yes, hi. Good morning. My name is Manasher Farkande. I'm the Program Manager for Advanced Technology R&D in the Office of Nuclear Physics within the Office of Science. We have 5 topics for our SPIR program. The primary mission of the nuclear physics program is to develop and support the scientists, techniques, and facilities that are needed for basic nuclear physics research and isotope development and program. Nuclear physics research is primarily carried out at national laboratories and accelerator facilities. These, as you will see throughout our topics in many places, are the CBAF CW Electron Accelerator at Thomas Jefferson National Laboratory, and RHIC, or Relativistic Heavy Ion Collider at Brookhaven National Laboratory, and also our office is supporting the development of a next generation rare isotope beam accelerator facilities, or FRIP. This is at Michigan State University, and you will see there are specific technological developments that this future facility needs, and there are a lot of the specifics, so particularly in the instrumentation and accelerator. We also have, of course, the Argon Tandem Linux Accelerator System, or ATLAS, at Argonne. Basically produces the stable and radioactive beams. Now, just one thing is that in our office, I'm the program manager for SBIR, and my name is the only, of course, a contact person listed in all the topics. However, within the office, we have people called top associates that they will be basically working with me, helping me in basically the review process and also selection process. You will not know their names, but we have people, they have more expertise in certain areas like software, instrumentation, and electronics, and particularly in in isotope. So if there are questions that I cannot answer now or later, certainly I can basically seek their help. Also, one thing is it was mentioned at the very beginning, that these technical details or topics are generated with the help of our NP community. So there are a lot of technical details that we list here, and if there are questions, again, basically we will be able to get help or actually talk to the person. I mean, I myself can talk to the person who actually submitted a specific request for a specific item in a topic or subtopic. One thing we did this year, at least for the NP topics, as you will see, is that we have in the subtopic, we have these references for subtopics. There are, in addition to the references at the end, within the subtopic references, we have names of individuals from our community that they basically are available in case there are questions, or particularly in getting more information on some of these complex areas of technical issues. You know, those names are there, but as I said, I remain the main contact. You can certainly, you're welcome to email me when you want to basically have a discussion with that particular person, but the emails are there. And before going through the top individual topics, I just want to say that the best way of communication with me is indeed email, because we travel a lot, so telephone is not always the best mean. So if you have questions or at any time, you can just simply email. The topic 36 through 40, this belongs to Office of Nuclear Physics. 36 is nuclear physics software and data management, and nuclear physics electronics design and fabrication, nuclear physics accelerator technology. 39 is instrumentation, detection systems and techniques. As you've seen a few minutes ago, HEP has something similar in all of these areas, so it is important that applicants or develop proposals, they look very closely on the detail. You just do not look at the general title of the topic or subtopic. You really have to look at the detail of what is being asked, because although these two offices, there are a lot of synergies, but clear differences, and needs are different at times. And then, of course, topic 40 is in nuclear physics, isotope science and technology. Now I'll go through the topics quickly. First, topic 36, this is software and data management. Of course, a large data scale of storage and processing are needed to store, access, retrieve, and distribute and process data for experiments. Now, nuclear physics experiments are done at accelerator facilities, and experimental data rates basically up to gigabytes per second, and the amount of data sometimes in some of these experiments collected, they reach basically hundreds of terabytes and sometimes petabytes. Now, on this particular topics, historically, the last few years, compared to other MP topics, applications in this area have not generally reviewed well, and thus number of awards each year for this topic are relatively low. And perhaps part of the problem is the lack of sufficient understanding of the complexity of the NP experimental data acquisition and data processing and the needs. So we clearly seek applications that demonstrate that understanding and the complexity. And as I said, we are interested in funding good and excellent proposals in this area, but of course there is no quota on each of these topics. So I think one suggestion is that on the subtopics for this topic, software and data management, they've provided in the references names of key individuals that if you want to get a better understanding, you can certainly talk to me, but also talk to these individuals. And the subtopics, of course, are large-scale data storage, large-scale data processing and distribution, grid and cloud computing, software-driven network architecture for data acquisition. This is relatively new, and so is the heterogeneous computing. Again, the first few are quite clear. Essentially, we're looking for incremental improvements. I think that's the key in most of these areas. One is not looking for some obviously you're looking for great ideas, but one is always looking for incremental improvements and methods to achieve what we want to do. On the software-driven network architecture and data acquisition, as I said, this is a very relatively new area, and it is basically, one example is development is required to implement the elements of this distributed data acquisition over commercially available network technologies. So again, the details are there, and there are individuals available and myself that if you have questions, as I said, email is the best way. And heterogeneous computing, this is essentially maybe a fancy word for use of GPU. This is graphical processing units in computationally demanding theory and simulation work. So essentially using GPU in areas that computationally are demanding. And details are there and name of people. There was a question in this topic. It was forwarded to me. And the question, I think, is a general question. So will the webinar clarify, refine the scope of the topic of interest? Obviously, the items of interest are described in detail in the subtopic. However, in my opinion, the scope of work, it is not discussed, and that is something that the proposals have to develop. And again, that depends, of course, on the phase of the phase 1 or phase 2. If there are questions, one can ask. But generally, the scope of work are not defined in the topic. So topic 37, this is electronic design and fabrication. Again, this is for nuclear physics. So clearly, as you know, the MP seeks development in detector instrumentation electronics with improved energy, precision, timing resolution, dynamic range, pulse shape discrimination capabilities, or any combination of these. Again, the emphasis here is the incremental improvements that are always state-of-the-art, number of channels, or again, sensitivity, resolution, and we're looking for improvements in the area, in these things. This topic is related to topic 39, which we'll get to it later, on the nuclear instrumentation. So clearly in the experimental, basically, apparatus, one needs, once a signal is generated, one needs to record and retrieve. And so that's where these electronic, basically, requirements come. An important criteria is the cost per channel of electronic devices. In this topic, each year we basically end up, again, after the process, reviewing the proposals, in phase 1, typically we get about 1 or 2 phase 1 grants. And while this is okay, but we are again interested into increasing the number of grants going into this topic. And we hope that we receive a stronger proposal in this topic. Subtopics are advances in digital electronics, circuits, advanced devices and systems, active pixel sensors, and manufacturing and advanced interconnection techniques. And of course, we have subtopic other. In the advanced in digital electronics, as you all know, digital, basically, signal processing electronics is replacing, in many areas, analog signal processing. And the key, of course, is essentially, in particular in nuclear physics, we want to determine the position of interaction points, for example, to an accuracy smaller than the size of the detector segments. And for example, for timing, essentially decision of 500 nanoseconds with resolution of 100 picoseconds. Emphasis is on circuit technology with low power dissipation. So that is a key element, because as you can see, we have these large detectors. There are hundreds of channels, thousands of channels, and obviously area is confined. And certainly, removing the heat generated by the electronics often is not easy. So that is an important factor. Circuits, this is listed specific circuits for various applications. In NP experiments, we listed them in the topic. And interest is in circuit operating in room temperature and in some specific cases at cryogenic environments. And specific types of application are mentioned, listed. Advanced devices and systems. This primarily is developing essentially new material or new electronics with band gap semiconductors. These are band gaps greater than 2 eV, like silicon carbide, gallium nitride, and so forth. Now, one important thing I often see is that it is important that the applicant demonstrate that there is the fact that we talk about silicon carbide or gallium nitride. There are applications in other agencies, in other industry, for NASA, for NIH, for Homeland Security. Those are fine, but it is important that one demonstrate that this particular development is for NP experiment and a specific NP experiment. It is fine that it has synergy and applications in other areas. That's quite fine. In fact, that increases the chance of commercialization. That is always encouraged, of course. But it is important that when this thing is there, if somebody says, well, this is great for a need for NASA, well, that is very good, but that is not sufficient. And that's one of the reasons often these things, when they may get phase 1, but phase 2, they may not basically pass the muster test simply because it has to show that it's also relevant for nuclear physics experiments. Subtopic D, advanced pixel sensors. As charge-coupled devices or CCD are quite common these days in basically in imaging devices. But these are finding their ways into nuclear physics experiments, and so the cost is an issue, and also signal to noise is an important factor. So this is an area that specific examples are given, and there are already some active phase 2 grants in this area, so this is an area of quite interest. Subtopic D, manufacturing advanced interconnect techniques. A large number of manufacturing techniques are listed, which are important to nuclear physics. There was a question. So one important issue here is that one has to realize that detectors are in several square meters at times in various NP or high energy physics experiments. So one has to make sure that all these interconnects, all these various pieces have to be connected together and where they sit. So there are a lot of detail that although something you develop is small, it has to be duplicated in many areas and many confined areas. So it is important that if there are questions, you ask me or contact one of the people listed on the subtopic. The references. The question was, will this program support TRL 0-1 fundamental research? If I understood the question correctly, fundamental research, of course, is funded by DOE Office of Science through other FOA, not through SBIR. For SBIR, it primarily is R&D for specific technology. I guess I should go a little faster. Topic 38 is nuclear physics accelerated technology. This is primarily technical needs needed for the NP facilities like CBAF and RIC and ATLAS and FRIB, which is the future facilities. And these are, again, technical areas that one is looking for incremental improvements which includes not only hardware but also simulation. Subtopics, you see material and components for radio frequency devices. This is, as you saw earlier, HEP has a similar area, so it is similar subtopic, so it is important that you look at the detail and see what are the interests, particularly on the range of frequency that our office uses for SRF. It's different or could be different than HEP or basic energy science accelerators. The key thing here, of course, is that, and then the radio frequency power sources. One is always interested in more efficient or wall plug efficiency of power sources. These include Klystrons, IoTs, and so forth. And again, examples of it given, and there are clear frequency range and power range are listed, and also name of contacts. And design and operation of radio frequency beam acceleration system. These are sometimes one is looking for novel ideas to accelerate new methods for accelerating charged particles, particle beam source and techniques. There's a very detailed list of technical needs are presented. These include simulations for beam physics for next generation facilities such as electron ion collider. Polarized beam sources and polarimeters. These are primarily techniques for components of a spin polarized proton, light ion and heavy ion and electron sources. So these are again looking for polarized beams. And this is primarily relevant to CBAF and REC. Charge stripper for heavy ion accelerators. This is primarily simulation work for charge strippers. This is related mainly to FRIP, Facility for Rare Isotope Beam at MSU, which is under construction. Rare isotope beam production technology. This has to do with technology with FRIP. And if you look at this subtopic, there are several specific technical developments which can have certainly, because of their nature, could have good potential for commercialization, and very detailed, very specific, contained kind of technical challenges. I encourage you to look into detail, and if questions there are, you can ask me or the person listed on the subtopic reference. And then, of course, accelerator control and diagnostics. This is essentially about beam monitoring and control devices, primarily for MP accelerators, but also with potential for use in industrial and other areas of accelerator use. There was a specific question about what is the temperature requirement for fast release solid catcher material. And depending on the catcher material for fast release, the temperature has to be just below the melting point, but very close to it. And example for tungsten is 2000 to 2400 C, niobium and tantalum are 2000 C. Nuclear physics instrumentation detectors.
Just a second to mention, we did receive one question on 38H. Okay. What type of data is currently being logged or recorded for accelerator components? What accelerator components of interest to monitor, and is structural health monitoring considered? This is related to your...
Yeah, so there are, as you can imagine, these accelerators have thousands of, sometimes tens of, thousands of components, and there are basically control system. One of them is EPEX, as not all DOE accelerators, but most of them, and also at LHC or Europe, they're using it. And the frequency that some of them are slow in a matter of basically at few hertz, or some of them even one every few seconds. These are, you can imagine, thousands of detectors, currents, temperatures, voltages, just you name it. If you've seen in the control rooms in some of these accelerators, and one shouldn't be intimidated because there's always room for improvements. But it's just thousands of signals, are primarily in forms of voltages and currents and temperatures. And again, we can discuss offline. But what is quite common these days is EPEX. If you actually go Google search for EPEX, you can find basically examples and the screenshots that you can see that will give you an idea. But again, it's just primarily those are the parameters.
And the EPICS is just
Yeah.
to clarify for the...
Yes, it's experimental. It's basically a name. It's an acronym. I'm sorry. It's a well-known acronym for a control system developed at various labs, and it's quite common, and it can be reproduced at other places. It's basically a control system. I would consider it as a slow control system that you can essentially distribute farm out and essentially allows you to collect data on any instruments you add to your detector, a magnet, a pressure transducer, or current monitor. Essentially, there are a well-established software and hardware that you can essentially collect data.
And that's EPICS?
EPICS, let's see, I'm sorry, it is EPIX.
Oh,
Right, I believe that's what it is, yes.
Okay.
Nuclear physics instrumentation, detection system, that's topic 39. This topic was completely rewritten this year for MP to ensure that outdated items are not in this topic, and the topic organization is improved drastically. This was done with help of a panel of experts in instrumentation from the MP communities. And we had in mind commercialization aspect in this when we wrote it. And as you see, there are subtopic A through L. I cannot go through all of them. They're basically, the first one is, I just go through their top actual title, Advances in Detector and Spectrometer Technologies, Development of New, Novel Fast and Solid-State Detectors, Technology for Ray Decay and Ray Particle Detection, High-Performance Scintillators, Shrink of Materials and Other Optical Components, Specialist Target and Nuclear Physics Research, Technology for High Radiation Environment, which has to do with FRIP, and of course we have other. There are also two technical transfer opportunities that I will not cover here. Just a few comments on some of these. The key thing is that we are looking in advancements in various areas. Obviously, we don't expect somebody to come and design a new detector, but it's just simply advancement, incremental improvement and advancement, which also is would be helpful for in case of commercialization. In terms of technology for ray decay and ray particle detection, these are primarily techniques that are needed to for experiments which are looking for very rare decay, like for example 1 true signal per year, which with a lot of background. These are primarily detectors underground, and one of such an experiment is called double beta neutrino-less double beta decay, and primarily one is looking for ultra background techniques, ultra low background techniques and materials, cost-effective production of large quantities of ultra pure liquid scintillators and methods. The technology for high radiation environments, as I said earlier, there are many specifics for this. This has to do with FRIP, and these are very basically well-defined technical challenges that FRIP is seeking basically to work with the companies to solve some of these challenges. The last topic, topic 4, your isotope science and technology. The isotope program produces isotopes that are in short supply in the U.S. and which there exists insufficient domestic commercial production capability. So this is the key, that our program has a mission mandated by Congress that only get into production and developing methods of production for the isotopes that are in short supply. There are some areas like molybdenum-99 or like some other areas that they are outside our jurisdiction. They are under National Nuclear Security Administration, or NNSA. One important document, in case you have questioned that what isotope is basically are included here, in addition to those are listed in the topic or subtopics, are that there is this called Nuclear Science Advisory Committee Isotope Report, or NSAC-I. If you, we have the link is there. You can look. There's a list of what this was basically a report in 2009. It still is quite valid. And there was, in fact, a question by someone on this webinar that was asking, for example, will a program to gather and purify radium-226 will be considered here? And I talked to my topic associate in this area, and the answer was no. Radium-226 isotope is not listed in the NSAC isotope report of 2009, therefore is not included. So mainly the two subtopics are, there are two only as you see, novel or improved production techniques for radioisotopes or stable isotopes, again, are in short supply. So first one is in the improved production technique. The second one is improved radiochemical separation methods. So these are the two areas, and there are a lot of examples there. And the key thing again here is that has to be on an isotope which is listed on the NSAC-I report. There were numerous questions about one of them. It was, I think, a general question whether is it possible to work with DOE laboratories or SBIR with private industry and academia. The answer is yes. There was a question about high temperature gas reactor that producing power. That is not part of the NP. SBIR, it could be part of nuclear energy, which is release 2, I believe. And there was also a question about how can we get DOE funding for our fusion energy research. That, again, is not part of NP. It's release 2 with the Office of Fusion Energy Sciences. And there was a question about would the radiation-hardened standard cell library be of interest for the design and fabrication of radiation-hardened circuitry? The answer is the radiation-hardened of electronic circuits is related to topic 37, which is electronics and circuits. So the answer is no. And basically, this is not listed as item of interest in either isotope or electronics and circuits. So I think I stop here. So any other questions?
Manisher, thank you very much. I think you covered that quite extensively. Anybody who has any questions for Manisher on his nuclear physics topics, please get those into him directly, and he'll make sure those questions are answered. And we have, I just want to remind you that this is the web link for this recorded webinar will be emailed to you shortly following this webinar, and that the funding opportunity announcement for these topics will open on August 12th, and there will be a webinar for the funding opportunity announcement and for your general questions as well, following shortly thereafter on, I believe, August 16th. So stay tuned for that. Manny, would you like to say some closing words?
Again, just thanks for everyone who attended today, and I know some of you have attended for a few days covering many of the topics in this solicitation. So thank you, and then again, please, for those of you who found this useful or have other ideas, we're certainly open to any comments and suggestions to improve the the quality of the proposals we receive. So thank you.
Thank you all very much, and this concludes today's webinar.